coding details about using Huggingface transformers. And the example would be to use the Huggingface transformers to classify the movie review from IMDb. And the problem setting is still a sequence classification. You give the model a sequence from that is a movie review, and you want to decide whether this movie review is positive or negative. And the label is his binary classification label, so either 1 or 0. 1 means that this is a positive review, and 0 means otherwise. And I will describe 4 parts: data set, tokenizer, models, and some small details in the training loop. So let's first install the packages. So if you're using the Google Colab, then we usually need to install using the pip install. But in front of the pip, we need to put an exclamation mark. But in the CS lab, you just need to do the Python 3 -n pip install in your environment. So the reason why CS lab does not allow us to directly call pip install is that there are multiple versions of Python. Actually, there are a lot of versions. And if you just say pip, then it's ambiguous which version of Python it is referring to. So we need to specify Python 3 -n pip install. But in the Google Colab, the default Python version is Python 3. So we can just say pip install. Now the transformers and dataset packages are installed. So both packages are provided by Huggingface. And they are really good packages. They are really convenient, centralized packages for us to either use the transformers and to load the natural language processing related dataset. Then let's import the packages on NumPy, Torch, transformers, and we're going to use the PyTorch data loader. And in the transformers, we're going to use the auto model for sequence classification, auto model, and auto tokenizers. You can see that these packages, these classes start by name auto. These are some convenient classes provided by the Huggingface transformers. And in initialization, you can specify the name of the model, and then this model will become, for example, a BERT model for sequence classification, and BERT tokenizer, or Roberta for sequence classification, and Roberta model, Roberta tokenizer. This kind of flexibility is allowed by the auto model. Also, for the datasets, we are going to import the load dataset function. This is one of the few APIs that are included in the datasets module. But this is, at the same time, one of the most useful functions out there. So we can just load dataset by specifying the dataset name, in this case, IMDb. So the IMDb, after downloading, we can print out the dataset and take a look at what it contains. So it contains a dataset dict, which contains 3 splits: train, test, and unsupervised. So this setting is slightly different from what you saw in assignment 3. In assignment 3, the IMDb dataset it contains train, validation, and test. And the train and validation set contains labels, but the test set do not contain labels. If you open the test file, the text.txt, you will see around 400 rows. And at every single row, the so-called label is 0. And this just means that it does not contain label. So it's neither possible nor necessary to include to report the results on the test set. So you only need to report the result on the training and the validation set, as well as some other training details. For example, your hyperparameter and how do you arrive in that hyperparameter. So for this data, you can take a look at the the corresponding split. In this case, we're looking at the trend split. You can see that there are two features out there, and the 25K rows in the trend split. So you can also visit an item by index in the data set, like trend 0. So this is a dictionary with two keys, text and label. So the keys correspond to the features described here. And you can visit up to the 25,000 example. So you can also visit a slice of items by a slice of index in the data set. For example, the first two items, or you can visit the first two items by this, and the output is still going to be a list. It's still going to be a dictionary, and the keys for that dictionary containing the two items are still text and label. But what's different is that the text here is a list of strings versus just a string, and the label is a list of integers instead of just an integer. So yeah, that's essentially how we navigate in the Huggingface dataset. It is also possible to export the dataset into CSV files or pandas data frames or pi-arrow structures. The Huggingface dataset allows a lot of flexibility. So any questions about the dataset itself? Okay, great. Let's take a look at the tokenization. So in this tutorial, we're going to use the bird-based case tokenizer. So to select the tokenizer, we are using the from pre-trained method. So if this is the first time you run this method, you will download the corresponding vocabularies. But if it is the second time, that you will directly query from the cache. So it is much faster. So in the previous hour, it took me like 10 seconds to download the vocabulary, but now it's just finished in a split second. So one traditional way to do the tokenizer is to first tokenize and then convert tokens to IDs, and then convert. Let's say the input is a string. Let's do tokenization. And the output of the tokenization step is a list of tokens. So you can see that the punctuation is split out as a standalone token. And the word tokenization is split out into two parts. And in the second part, this token starts with two hashtags. So this is a special character brought in by the bird-based case tokenizer. So if you are using the Roberta tokenizer, then you will see that for those tokens that are not split out by from the words, these non-special tokens will start with a symbol that looks like G. So the behavior of different tokenizers are actually different. So please be really careful when selecting the tokenizer. And we should actually take the tokenizer that is provided by the model developer. So for example, if you're using the bird-based case model, then you should also use the bird-based case tokenizer. So the second step is to just convert the tokens to IDs. And you can see that the IDs are a list of numbers, the list of integers, and these integers correspond to the indexes in the vocabulary. So you can also convert back the IDs to tokens. And you can see the list of tokens again. So tokenizers have some special tokens. You can query what those special tokens is also by convert IDs to tokens. So usually there are a lot more special tokens than the special tokens shown here. Here I'm just giving some examples. I'm just printing out the first 6 special tokens. And vocabulary location number 0 is designated as the path token, and the remaining 5 are unused. So some other commonly used special tokens include the start of sentence and end of sentence, and the COS tokens, and they might be located at some other positions in the tokenizer. Of course, we can use the tokenizer in one line. We can just call the tokenizer and pass in the sentence. And it is going to output input IDs, token type IDs, and attention mask. So the token type IDs are not very important here. So I'm not going to go into the details of token type IDs in CSC 401. But the input IDs and attention mask are really important. So we usually want the tokenizers to output PyTorch tensors. So this can be specified by designating the return tensors to be the PyTorch tensors. So now you can see that the input IDs are 2-dimensional PyTorch tensors instead of 1-dimensional list. But the element values are still the same. So here you can also specify the return tensors to be, let's say, the JAX tensors or the TensorFlow tensors. Continue and see how much we can cover in the remaining of this tutorial. So actually, this Python notebook is already online. So even if we are not able to cover everything, you can still play around with this notebook. And the link is on the course website. So let's try to tokenize a batch of sentences. You can specify the padding and pad the shorter sentences to have the same length as the longer sentences. So if you specify padding to be true, then it goes to the default behavior, which is to pad the shorter sentence into the same length as the longer sentence. Actually, the longest sentence in the batch. So you can see that the longer sentence have one more token than the shorter sentence. So in the end of the shorter sentence, you can see there is a padding token at the end. And similarly, at the attention mask, you can see the end of the first sentence is specified with a 0 in the attention mask. So the purpose of 0 here is to knock out the effect of this token. So whatever you pass in as the last token, if your attention mask is 0, then the input actually doesn't matter. The impact is already knocked out. So you can also see that an alternative method to specifying the padding is to specify it to be the longest, and the behaviors are the same. So you can also pad it to a designated length. So for example, specify it to pad to the max length, and max length equals to 32. Additionally, you can also specify the truncation. So truncate to a maximum length. So any questions about the tokenization and the padding for the sequences of different lengths? Okay, great. Let's take a look at the models. So there is an analogy between the Huggingface models class names and the assignment 3 class names. So in Hugging Face, this is called auto model, and in assignment 3, this is bird model. Hugging Face auto model for sequence classification is the bird scent classifier in assignment 3. So if you are not sure about the implementation, you can check out Vaswani's paper. And if you are still not sure about the programming details, you can check out the corresponding implementations in the Hugging Face GitHub. But do not copy-paste the Hugging Face implementation because the variable names are different. So you can print out, you can load the model by the from pre-trained method. And you can print out this model to see the components. So you can see the bird model contains an embedding component followed by the encoder. And this encoder contains 12 layers. And each layer is the QKV attention, add norm part, and then another dense layer and another add norm part. So in each of these components, you can see that the input feature and output features and the specifications in the dropout and also the activation functions. Transformers like to use the GALU activation function, the Gaussian linear unit, instead of the ReLU activation. So there are some papers saying that the Gaussian linear unit are achieving a lot better performances than the ReLU activation. Yeah, you can see that the layers are sequentially connected. So the output of the previous layers are the input to the next layer. And in the bird-based model, there are 12 layers of this kind. And at the end of the 12th layer, there is a puller. So the reason why people use this puller instead of the other output, like the output for the other tokens in this sequence, is essentially empirical reasons. So people found that using the puller leads to good performances, and there are actually a lot of other papers that experiment with different outputs, and none of them have significantly better performances than the models using puller layers. So people just follow the conventions and continue using puller layers. You can use dir, the directory command, to take a look at what the bird model contains. And some of the important functions include the eval and train and CPU CUDA device, and here's the eval. So before the evaluation loop, you need to call model.eval so that the gradients do not accumulate and something like dropout can be properly handled according to the specifications in the evaluation. And there's also the function to. So you can call model.to some particular device to shift the model's parameters from and to the CUDA. And also, if you have multiple CUDA devices, you can specify it to be a model.to CUDA colon 0 or CUDA colon 1 to specify which device to move these parameters of this model to. And to check out the names of the modules, you can specify. You can visit them through _modules, and this is only recommended when you are debugging the model and not deploying the models, because in Python, every single element in the module, in the classes, they are public, but for those elements that are not supposed to be that the developers don't want to be publicly visible, they specify with an underscore at the start. So you also take a look at some shapes of some parameters, like the embeddings. You can just visit them by calling out the names. And you can see that BERT contains 3 types of embeddings: the word embeddings, position embeddings, and the token type embeddings. But GPT-2 only contains 2 types of embeddings. So you can also visit one particular layer. So in each layer, there's the QKV attention, the add norm component, and the intermediate part, and another add norm. So let's take a look at the BERT with classifier head model. So BERT for classifier head is essentially an auto model for sequence classification. So this contains a BERT model and a classifier head. So after this BERT model, there is the dropout and then classifier. So again, you can also look at the corresponding elements using the directory function. So in the BERT with classifier head model, you can visit the BERT part using the BERT element. So the BERT element is essentially a BERT model. And there are also the dropout module and the classifier module. So the BERT module is a BERT model. So there are the embeddings, encoder, and the puller part in the BERT model. So for the input and output specifications of the auto model, it takes in the input IDs, which are PyTorch tensors, and output last hidden state and puller output. So the last hidden state contains shape, batch size, sequence length, and the hidden dimensions. For BERT-based models, they specify the hidden dimensions to be 768, which is a popular number in machine learning. And the puller output has dimensions batch size times hidden dimension size. And in the implementation of classifier, we just take the puller output and pass it into the classifier, the linear head. And then at the output of the linear head, apply the log softmax. So do not apply the softmax before the linear head. Instead, you need to apply the log softmax after the output of the linear head. So that's another confusing part of the comments in the classifiers.py. You can also specify the model to output some additional contents by changing the configurations, like output attentions equals true. Then it outputs attentions in addition to the last hidden state and the puller output. So the attention contains 12 layers, and it's actually a list of number of layers of PyTorch tensors, and each PyTorch tensor has size, batch size, number of attentions, and sequence length times sequence length. So 7 here corresponds to the sequence length, which equals 7 here. So if you use another sequence, like this sequence, the sequence length is 5, then the attention's shape becomes 1 by 12 by 5 by 5. Okay, is there any questions up to this point? Okay, great. Let's take a look at some small details in the training loop. So in training, you will need a data set and a data loader. A data set is essentially a list. And the list supports querying the total length, which is supported by the underscore underscore len underscore underscore method. And also, the list supports visiting by index, which is supported by the getItem method. And the next important element is the data loader. You can specify a data loader that gives you one batch of items at a time, instead of an iterator, which gives you one item at a time. So range n gives you an iterator. This gives you one item at a time. But a data loader gives you one batch at a time. Let's say we put this data set into a data loader and specify the batch size to be 2. Then we can iterate this data loader and print out the batch to see that each batch is actually a collection of 2 items. You can also specify the batch size to be like 3, for example. And then you can see that each batch contains 3 items. So in each batch, the number of batch size items are collated to each other. So PyTorch data loader has a default collate function. So if you do not pass in the collate function, then it automatically concatenates them and outputs a PyTorch tensor. But if you want to do something fancy, you can specify the collate function. And here, I'm specifying the collate function by a very simple operation. And this operation is just to add 1 to every single items in the batch. So I'm still using the data set of numbers from 0 to 10, and batch size specified to 2. So you can see that every items are added by 1. So the things that are usually recommended to do in collate functions are the shifting between devices, like from the CPUs to GPUs and between GPUs, and some paths if you are not tokenizing them before. So the last thing I want to quickly comment on is the cross-entropy versus NLU loss. So a cross-entropy loss is essentially an NLU loss followed by log softmax. So they are the same thing. But if you Google online, you can probably see a lot of tutorials that use the cross-entropy loss. But in assignment 3, we're using NLU loss. NLU loss, so you need to add in the log softmax part in the classifier.py before passing the output into the NLU loss. So we can verify that the output of the cross-entropy loss exactly equals the same the output of the NLU loss followed by log softmax. So yeah, that is all the contents of this tutorial. I think you already have enough, up to now you have enough material to start working on assignment 3. And we will cover material for doing assignment 3's first question next week, which is the speech recognition. And the questions 3 and 4 are about implementing BERT models. And I think you can start working on that now and this weekend. So if there are any questions, feel free to post on Piazza. And TS and I will try to reply as soon as possible. And see you on Monday.